Alright, hell yeah. I'm going to tell you how long this video is in the description right here, and then we're just going to fly through these. Now, if I want to dive deeper into a deeper understanding, we'll put it at the end. We can make a 3-hour video here, but this student wants these 4 problems done. These might not be the exact problem that he has in his book, but they're close enough because, hey, they have to deal with trigonometry and U substitution, so they're not trivial. And so I'm going to try to put little tidbits in the fly, but man, we really have to crush this out, and I really want to make a video that does crush it out. Okay, so U substitution says, hey, let's choose that as our U. Why? Is because, you know what I mean, I've memorized that I know what the cosine of U, sorry, getting ahead of myself. I know what the cosine of x is, you know what I mean? And this is where we got into the rabbit hole. But I'm going to draw my sine graph, sine of x. Looks like this. Slope of 1 goes to 0. So what equation starts at 0 and goes to 1? That's going to be cosine x. So the derivative of sine x dx is cosine x. Therefore, the derivative of sine x plus a constant dx is still, when you take the derivative of a constant that goes away, is cosine x. And this is literally the way you should be learning integrals, because now I can say the integral, oh, and check out this. Hey, you can even move this dx to the other side. A lot more has to be done, you know, in this realm where you're just like, hey, let's use this, you know, so it looks like math, where you're just like, oh, that makes sense, but don't quote me on that thing. But if you have the integration of cosine x dx, that is going to equal sine x plus cosine. And so, therefore, we know what the perfect, we're done. And there's 2 of these with a plus and minus. You know, that's what we can add at the end. But let's move on. So we do know that the integration of cosine x is going to be sine x plus a constant. Alright, hell yeah. I don't have cosine x. I have cosine 8x. So this is where I'm just going to say, hey, my u value is 8x. And then I'm going to take the derivative of u with respect to x. I think here's a good tip when you're taking derivatives. Do this, d, and then put this in parentheses. You know what I mean? And then, like, what is this? It's 8x. And then we have the derivative. And I don't know, even just put this value in parentheses. And so, and we can maybe do that as we go today. And, shoot, we have a constant. So even this one, your rules of differentiation says you can bring the constant out. And we have dx and dx. Now, this is our function. Our function just is this value that x changes like that. And when we change this independent variable here, 0, 1, whatever, you know what I mean? So that kind of spells it out, but also they're the same, and we have a fraction, and so that is just 1, so we're left with 8. So now in this part of the game, we're going to have du dx is equal to 8. Here I would say, hey, we have 3 things. This is my strategy from physics. This, my brother, it's not numerical methods, I'll think of the term. But it's, but hell yeah. If I have three different things with one equation, I can rearrange this 3 different ways. You should. So let's solve for dx. dx is du over 8. All right, so we solve for 8, we solve for dx. Let's solve for du just for the heck of it. Du is going to be 8 dx. Now, which one of these are we going to use? We can use them all. But what did we do to our original equation? We took cosine, we put a u here. We haven't done anything with this dx. It's still like that. And so I have, you know what I mean, 2 variables that are different. I can't take the cosine, I can't integrate cosine u dx, you know what I mean. So let's, but this is, I can just sub this in. So there's our dx, and let's see if it works out. And so we have cosine u, and then we have du over 8. Let's, a couple ways to do this. You could put this is a 1/8. You could put that right there, and you could just put it all the way outside the integral. So we have cosine u du. And now we have something very similar to cosine x dx, which we know the general formula of. And so that's what we're going to do. We're going to say that's going to be 1/8, and then the formula for this is going to be sine, and if we do it in terms of this variable u, it's going to be sine u plus a constant. So we're going to have sine u plus a constant, and then hell yeah, that's the answer. U, since we said u was 8x, we're going to sub that back in. So we're going to have 1/8 sine of 8x plus a constant. And now, cool, now we get to actually see if this works. Let's say I made some mistakes, and who cares if I did. The whole idea of this is I'm going to differentiate this with respect to x, and this is 1/8. And let's get a whole new sheet of paper. If we think this is our actual answer, this is worthwhile going over on each of these. And then we can see if we can kind of bust the next one a little bit faster. But I'm going to try to take the derivative of this with respect to x. Again, like, hey, maybe I know how to take the derivative of sine x, but that's it. I don't know how to take the derivative of sine 8x. You know what I mean? But, and this is the fundamental of the chain rule that, you know, should just be, you know, so easy. So let's first, you know, actually, yeah, I mean, this is a bunch. So let's kind of simplify this. We're going to, you know, pop out the constant, take our change, and then what is this change in? Use parentheses. This is change in sine 8x. You could even plug in some numbers. And, you know, this is a function, so I'm going to plug in a value and then get something. This is like, you know what I mean? And then I'm going to change x by one value. I'm going to go from 0 to 1 and then get a new value. And what this derivative says, I'm going to take the change in this. So if this is the second value, this is the first value. I'm going to take the second value minus the first value divided by the change. And the change was 1. So that's always a great way to do it, especially if you can change something by 1. Now, changing by 1 radian is kind of huge because, you know what I mean? Like when you're dealing with trigonometric functions, this x is in radians, and that sucks because, you know, always good to, you know, draw a triangle. 1 radian is about 60 degrees, and why is that? You know, this is kind of the rabbit hole I get down, is that radians gets, they're defined by taking a circle, measuring a string the length of the radius, and then draping that string around the circle. And you'll get to there. You'll get to about 60 degrees. That's going to be 1 radian. And it's a type of angle. So we're used to degrees, and so this is an angle in degrees. It's about 60 degrees. That's the degrees in radians. It's radians. It has its own term. But that's what it is, and that's 1. So half is going to be there. That's about 30 degrees. You know, that's half. And then so what about a tenth of that? So 0.05 radians would be 3 degrees. Okay, hell yeah. So you would really have to find a value at 0, you know, x is 0 and then x is 0.5 to actually, you know, get this, whatever the hell that is, and then say your change down here is 0.05 minus 0, and that actually gives you a value. So that's one way to check. Like I said, at the end of this video, I don't know if I've said this yet, I am going to double check these with the calculator, because what we have is this equation should have, for every value of x, it should have a slope. You know what I mean? So if I have this equation, it looks like that. I'm going to go right there and then use my solver to find the slope. And so what I did is maybe I put in x is equal to 2, and I get the slope is 3. Cool. I'm going to take this value of 2 and then put it into this, after we take the derivative, into that equation, x is equal to 2. And that should give me y equals 3. So, yeah. Alright, brutal. But yeah, so let's, what are we doing? We're trying to simplify this. 1/8 sine 8, yeah, let's redo this. So we got 1/8 sine 8x plus a constant. We're going to take the derivative with respect to x. I'm going to using my rules of differentiation, the constant comes out. Derivative using these parentheses, sine 8x with respect to x, plus and I can take the derivative of this. We're going to do this in 2 steps. The constant comes out, derivative with change of 1, and at the end of the video we kind of talked about how you can. This is still a function. There you go. This is 1. This is the function. Y is equal to mx plus b. Your slope is 0. This is y 0, x plus 1. So if you're just like, well, I'm changing x, but there's nothing to change. Well, yeah, there is, but it's just always 0. And so your change is going to be the same value, 1 minus 1. And let's say you changed x from 0 to 1. That's 1 minus 0. So you're going to get 0 over 1. You're going to get 0. So that's why the differentiation, the derivative of a constant when you change the independent variable is 0. And you can see this constant is, you know what I mean? This we just showed was 1, but obviously if you multiply by that constant, you're taking this graph and then multiplying it up a value of c. Alright, hell yeah. And I think people want this. I'm trying to like do it fast, and I'm sorry if it's just getting all over the place. Alright, so, but this part just goes to 0, hell yeah. We have a constant out here, but right here, I don't know the derivative of sine 8x. But maybe I can use this u substitution and say u is 8x, and let's do that. And here, but we're still changing x here. So this actually kind of explains the u substitution. At least I can explain it better from the derivative perspective. So when we do this, when I put sine of u here, and then we take the derivative as we change x, like, hey, I'm changing x, but I don't know what's going on with this u. And so the change in this formula, I don't know. You know what I mean? Big question mark as I change x. And so here's what the chain rule says. Well, let's do this. Let's take the change of this. And this is super similar just to sine x, which we know how it behaves. But we're going to take this. We're going to take the derivative of sine u with respect to u. We're going to change u. And then over here, we're going to take the derivative of u with respect to x. And this is the critical part to actually, you know what I mean, probably right here put in that this is 8x and then with respect to x. Because, hey, I can do that. You know what I mean? du dx. And so, hell yeah, break out the constant, dx dx. This is just 1. And so, hell yeah. And then so the derivative of this, we know that the sine function goes like there, slope of 1, slope of 0. What does that? Cosine. Cosine of u does that. And so this derivative is going to be cosine u. This term is just going to be 8 times 1. This term is going to be 8. And then so hell yeah, so that's the derivative of this. And then and, you know, we're missing this 1/8. Sorry about that. So we still, you know, this 1/8 never went anywhere. It's just outside the derivative. We're so focused on this derivative that we almost forgot that. After we took this derivative, we get this. We can, you know, let's show that 1/8 just to make sure we don't forget about it. And now we can sub in that u. So now we have 1/8 cosine 8x times 8. These 8's cancel, and we have cosine 8x. And does that make sense? We took what we thought was the integral, which is kind of like your, you know, 1/2 x squared. And then if you started with x, what's the integral of x dx? Well, it's that. So if you had this, and I took the differentiation of this, bring down the power, and then drop the power, you know what I mean, all that, then we get x. And so that's what we did here. If this is the integral, when we take the derivative of it, we should get this back. And so the integration of this dx is that, And there you go. So there's the first one, and hopefully we can do the next few in and maybe we'll do them in separate videos. But no, I just want to bust this out. So hell yeah. And hell yeah. Alright, hell yeah. So the next one up is going to be this one. Problem 37. 1 divided by theta squared cosine of 1 divided by theta d theta. Alright, so hell yeah. And in this, you just like, I don't know. Like, part of this is like you're supposed to just have an intuition a little bit and just guess. I mean, I don't know. You could have this be your u, and then you're going to strike out getting your du. Nothing's going to cancel, and you're just kind of... So for this one, we're going to have this be our u. But the first thing that I'm going to do, I don't like theta. I don't use it very often, and it's kind of a variable that doesn't matter. It's just a variable, but we're going to change it to x. So we're going to have 1 over x squared cosine 1 over x dx. And we can also do this. This is the same thing as x to the negative 2 cosine of x to the negative 1 dx. So all of these things, you get to choose kind of what, you know, what you're more familiar with and kind of looks like, oh, I can see some patterns there. So we're going to set our u is equal to... And again, I don't know the integration of this. You know, if I just had to integrate cosine of this, I don't know. You know what I mean? But I do know the integration of cosine x. And that's going to be similar to the first one. I'm not going to go over it. That's going to be sine x plus a constant. And let's just do a double check, because if we have sine... if we start with the sine x and we take our derivative of this, you know, we're going to get 0 and 1. That's going to be cosine. And so the derivative of this, if we took the derivative of this, we would get cosine. Therefore, the integration of cosine dx is sine x. And we can have a constant here, because if we take the derivative of sine x plus a constant, the derivative of the constant will be 0. Alright, cool. So now we're on board with that. Our u term is going to be, and I'm going to do like this, x to the negative 1. Because now we're going to do our du dx term. And that's going to be dropping the power. We're going to have a negative 1. And then we're going to drop this power by 1. And that's going to be, you know, this, and then negative 1 minus 1. And so that's going to be negative 2. Alright, hell yeah. And so that's just the power rule for... exponents. Heck yeah. We have 3 things here. You could rearrange this 3 different ways. We're not going to, because we know that, hey, this is what we're solving for. You know what I mean? So let's just do that. So dx and get this downstairs. And so, yeah, let's maybe do this in 2 steps, but downstairs is going to be the negative 1. Also downstairs is going to be the x to the negative 2. Cool. So if this is downstairs, we can move it upstairs. You know, because this is the same thing as 1 divided by x squared. So if we have 1 divided by 1 divided by x squared, that pops upstairs. Hell yeah. So if you have this, so yeah, so let's do that. So we're going to have, and the negative 1, if you have a negative, you can put it in the numerator, denominator, it doesn't matter. Let's just put it in the numerator. So we're going to have negative x squared. So that's our dx term. And we still have this du. Sorry about that. That's very important. Okay, so now when we plug these in, I'm going to have, and this is where the magic happens. You know, you're supposed to take something and it's supposed to simplify down to something we can integrate. I can integrate a cosine u du because it's identical to integrating a cosine x dx. That's kind of the whole basics. Like from the, we're just supposed to know a few trigonomic, we're supposed to know first how to differentiate trigonomic functions. And I'm not going to be able to get that sheet. Sorry about that. But hell yeah. And then once we're able to, you know, differentiate trigonomic functions, we can see that the reverse is the integral. Okay. Alright, so let's do the magic. So we're going to have this. We're going to have the integral of 1 divided by x squared, cosine of u, and then the dx is going to be this term. We're going to have, I'm just going to do a negative. I always do my negatives as negative 1s in parentheses. That's the way I don't forget about them, don't lose them. And they don't look like minus signs. And then I'm going to have x squared. And then we still have this du. All right, voila. What cancels? Hell yeah. So now we have something that's, and I'm going to get this negative 1 outside the integral. And then we're going to have cosine u du. So finally, we have something that's representative of this. I know how to integrate it. Keep the constant where it is. This becomes sine u plus a constant. And then put in the, so negative, and I'll just do negative sine, plug back the u, which is x to the negative 1. Now I'm going to say this is also 1 over x, just because now it visually looks better this way, maybe, plus a constant. And now let's do this one in reverse. So we have, we're going to take the derivative, dx, of negative 1 times sine 1 over x plus a constant. You know, again, we can do this. You're taking the derivative of the entire equation. We know that's 0. Hell yeah. Pop this out, and now we're taking the derivative. I know the derivative of sine x, so let's talk about that one. If I have sine function, it looks like that. And it's slope of 1, slope of 0. That's going to be the cosine function, because cosine function is this. And at the end, we do a better job of drawing these, you know. And but hell yeah, so that's the derivative of this is the cosine function. But I don't know what 1 divided by x, so we have to use u substitution. This is where we're going to say u is 1 over x, and then we're going to use the chain rule. We're going to say I'm going to differentiate sine of u. Don't forget about this negative outside everything. Differentiate sine of u with respect to u, and then du dx. And so this is where we still do this. Du dx is going to be d of 1 over x dx, and we can write this 100 different ways. We can say this is dx to the negative 1, and then I think it's useful to put these in parentheses. Sometimes, especially in the mechanical engineering books, like everything will just be in parentheses like this. I think this is useful because it shows that, I don't know, this top one is a function. This is like your y equals, and y could equal x. I think it's useful to say y is equal to x squared, just so that they're not the same terms. So if I put in a 2 here, I get a 4 there. So this, you know what I mean? So let's do that. Let's go from 2 to 3. So if I put in a 2 here, I get a 4. Put in a 3 here, I get a 9. So this, you know, and then how do you find the change? If this is the change in, you know, the change in x squared, when I change x, that's what we're doing. You know, it's going to be 9 minus 4. That's going to be 5. So I have a change in 5, and all we did was change x by 1. And so that's going to represent the derivative very close to 2 to 3. And the derivative will go through this value somewhere between 2 and 3. I think that's one of the formulas. And, you know, just a mathematical x squared is great. You know what I mean? Because maybe you can make your table 1 meter wider, and you want to know what the change in area is. It's about 5. But what is it? You know, if you did take the derivative of x squared, you bring down the power, and then drop it, it would be 2x. And you wanted to take that. If you took the derivative at 2, it would be 4. If you took the derivative at 3, it would be 6. And so your change in area would be 4 or 6 or an average of 5, and that's what we're showing there. But hell yeah, and I think that does not get talked about of just like, hey, this is your thing, you know, this is your independent variable. I can concisely just change this incrementally, and then this might change wildly. That's what we're trying to figure out about the universe, you know what I mean? All right, hell yeah. And, all right, so just using basic rules of differentiation, we're going to drop the power and then drop this. It goes to the negative 2 and scene. We're done. So we have negative 1 divided by x squared. Hell yeah. So let's throw that in. So we're going to, and then we know what the derivative of sine u is. Derivative of, this is sine, slope, because the derivative is the equation that gives this value of the slope. This value of the slope right at 0 is 1. Value of the slope right at 90 degrees is 0. And that's going to be cosine. So I'm going to have cosine u, and then and the derivative of u dx was this, negative 1 x squared. And then my constant didn't go anywhere, and then I can sub the u back in. So now we have, so I'm going to say the negatives go away. I'm going to put this out front, x squared cosine 1 divided by x. Therefore, when we integrate this and change dx just by a little bit, and I'm not even going to touch the actual, what the hell is an integral, area under the curve, it's a value, and then change the value just a little bit, and it's going to be that little sliverly slice. But hell yeah, we did it. You know what I mean? So at least we went back and forth on that one. But yeah, this is the video of like, hey, this is a fast video for me, just kind of crushing these out. Alright, and maybe we'll try to do this one 2 different ways to see if we can run into some roadblocks. Alright, hell yeah. Alright, so problem number 3. And I would just do this one. I think I put this as u last time, but I think this one you can do anything. The whole idea is when you throw in a u here, I'm going to get like a du term. I'm going to take a derivative of this, and it should look like that and maybe cancel, hopefully. And I can't even tell you why these cancel so simply, other than the fact that they made these problems to cancel so simply. And that's where I don't really put a lot of emphasis in stuff like this. You know, it's good to know, it's cool to know, and you have to know it, and then forget it by the time you get on to engineering, because, you know, honestly, numerical methods is the way to go. Like, if this is your function, and you want to find some sort of area under the curve, and that's representative of, like, you know, what you're doing from mechanical engineering perspective, like, I don't know, like, what's your range of x? Maybe your x range is just here to there, and then you can easily just numerically find that area and find the values. You know, this is, that's all the only reason math is cool is because you get these cool, concise equations. But I don't know. I don't, like, even my brother doing quantum physics, you know, he's working with lasers, and he has a lot of, you know, yeah, he's working with quantum physics equations, and he's, you know, trying to find areas under probability curves. And you use numerical methods, like, get out of town if you want a lot of stuff to, you know, have a magical, you know, little, you know, formula that's what do you call, I don't know what you call it, but it's where you can just, you know, do mathematical properties in one go and then chisel out an answer. Alright, hell yeah, so I think I did this as u last time, let's do this as u. So I'm going to have u is going to be sine 2x. And again, this one is tricky because I've already used this term u, and I don't know what the integral of sine 2x is. I know what the integral of sine x dx is, and I know what the integral of sine u du is. And so, and I'm sorry, if u is this, I just need to figure out the derivative du dx. But I don't know what the derivative of sine 2x is. I only know what the derivative with respect to x of sine x dx is. So this is where you have to use that u substitution. And we're going to use it twice, so we're going to say this. We're going to say the derivative of, so I'm going to do u prime is 2x. So I'm going to take the derivative of u with respect to u prime, and then derivative of u prime with respect to x. And I would put parentheses in here, I don't know, let's see. So what is the derivative of u? We just said u is all this, so this is the derivative of sine, yeah, so I mean if you do it like this, you screw yourself over again, because you just have derivative of sine 2x, and you're trying to change this variable u prime. I can't take the derivative, nothing looks similar. So let's do this. We're going to take the derivative of u as we, and where are we at? yeah, I'm getting ahead of. So this was the first u substitution, and now we're actually going to have to use another u substitution. So that second u substitution will look like this: sine of u prime. So now this is what I'm trying to take I'm trying to differentiate sine of u prime. But it is useful to throw this in. And I'm not going to get into the fact that you're going to call this gx, and this is, let's not do that. Hell yeah, and we're going to differentiate. Alright, hell yeah, took a little break there. Okay, so we're going to set up the chain rule. So we now can differentiate with respect to this u prime, and then we're going to take, this is how the chain rule works, because these can cancel, and then hopefully this is our dx, sorry about that, hell yeah. So this derivative of sine is going to be cosine u prime, and then the derivative of u prime, I'm going to take the derivative of u prime with respect to x is the derivative of 2x with respect to x. Even on these simple ones, it's good to write this. Even take out the constant and then dx. And so that's literally, this is the function. I mean, this is a kind of a y equals x function where you have, there's your function x, and then here's your independent variable. And I think that doesn't get explained enough. When you're taking a derivative, you're having, something that could possibly change while you're changing an independent variable. This is very concisely going to, be, 0, 1, 2, 3, 4, 5. Now, it doesn't have to, the criteria on this, it doesn't have to be continuous from negative infinity to infinity. It just has to be useful and, at least decently continuous along like where you want it to be, where you're analyzing it. And so that's also good to know, just from the standpoint of why are we doing this and where does it work, where does it not work. Okay, so hell yeah. And that's just, when this changes, the y equals part changed by 1, it went from 1 to 2, so that's 2 minus 1, and this went from 1, and this went from 1 to 2, which is just a change in x of 1, so 1 minus 0. And so we're going to have 1 over 1, which is always 1. The slope of this graph is always 1. And then the constant, and that's where superposition comes out. This constant then just tweaks the graph into that. The slope of that is 2. Okay, hell yeah. So that is going to be du prime dx is 2. And so we're going to have a 2 right there. Cool. We might have made a mistake, but we're still pretty good. So now what was that? That was just the part to actually find du, derivative of u with respect to x, which we said, yeah, I'm not even going to go over that chain rule again, but that's how we set it up. There's going to be, we did, anyway. And that's just going to be, and then, let's put our value back in. So that's cosine 2x times 2. So it's 2 cosine 2x. That is the derivative of this, 2 cosine 2x. Now for derivatives, there's not another check where you're just like, oh, can I take the integral of this and double check it? I suppose you could. You know what I mean? I mean, we just took the derivative, damn it, and we are going to do that because we can use the same friggin' u substitution on this. Let's call it w substitution. I'm going to say w is 2x, and then so we're going to have, we're going to do the integral 2 times cosine of w dw, and so we're going to take dw dx. That's going to be 2, and then I have to take the integral. Sorry, if we integrated that, if we had 2 cosine 2x dx to integrate this, I just subbed this, so we have cosine w, but I still have this dx part. The dx, if I solve over here for dx comes upstairs, 2 comes downstairs. Let's write it as this, 1/2 dw. That might be the easier way to look at it. Sub that in, and we have, and this is still just the integration of 2 cosine w 1/2 dw. You can see the 2's cancel, and we have the integration of cosine w. And we know what the integration of cosine, do we? You have to figure out what your differentiations are. So we're going to take the sine graph and differentiate it, and we're going to see that it's 1 and 0. That's going to be cosine. So sine, differentiation of sine goes to cosine. Therefore, the integration of sine, or of cosine x dx, is sine x plus a constant. And so the integration of this is sine x plus a constant. And so we're going to have sine w. Let's just throw everything back in with 2x plus that constant. And hell yeah. What did we just do? I don't even know what the hell we just did. But I really don't. We were trying to integrate this, and we got sine 2x plus a constant, which was that. That's what we did. But hell yeah, that was headachy. I don't know if that's actually useful for this video. I usually go twice as slow maybe, but I'm purposely trying to crush this out, but mistakenly just going down these little rabbit holes. Alright, so let's start fresh and get back to that point. Because that's the other thing with math, physics, calculus, just all these subjects. I like to think of them as like juggling. So here's my u value. U is sine 2x. I need to take the du dx of this. Maybe I don't know it, but sine of u, I could take the derivative of that with respect to u, and then take du with respect to x. And then so this is a new u. This is for sure a new u. And then so that u is going to be 2x. Du dx is 2. So I have a I have a 2 there. I know what the derivative of sine is. That's going to be cosine. So I have cosine. I'm going to have 2 cosine. The u, plug it back in, 2x. So there you go. So that's is probably overkill, but it's good to go through those u substitution fundamentals even on something like this. So we have 2 cosine 2x. Hell yeah. Now, this was our u substitution for this. So this now looks like this. U cosine 2x dx. So let's solve this for dx. So dx, upstairs, downstairs, is going to be, I think that upstairs, downstairs, I just put everything downstairs right off the bat. Hell yeah. And then kind of rearrange this. It's going to be 1/2 du cosine 2x. And you could even, I would separate. Usually this you want to separate, but I could do this 1 over cosine 2x and then put the du right there. So that is what we're subbing in for this dx. So we're going to have the integral of u cosine 2x. I'm going to put that in parentheses. This dx is coming in hot, and we're going to have 1 divided by cosine 2x. See how those cancel? That's going to be the juice. And then we have this du. And the whole thing about this is we can't integrate the u du part. Those cancel. Let's break out the constant, 1/2, and then we have u du. Hey, I can do this. Power rule, integration. That's keep this. The u goes to a 1 plus 1 divided by 1 plus 1. So that's going to be a 1/2, and this is u squared divided by 2. It's going to be 1/4 u squared. And hell yeah. And so put back our u term, and our u is this. So the integration of this, and then we're going to have plus a constant, is going to be 1/4 sine 2x all squared plus a constant. Now, they're going to probably have you write it like that, which is just mind-numbing. I like it like this. If you're doing squaring, cubing, trigonomic functions, man, it can just be, for your first 1,000 go-arounds, this is such a better way to show that than this. This is a disservice to the up-and-comers. I think it's a disservice to the learning trig. Alright, plus a constant. And hell yeah, we did it. And so for this one, we're not going to do it in reverse. You could do it in reverse, but what we are going to do is use substitution the other way, and we should get the same answer. So we're going to say u is cosine 2x, and then du dx. So I don't know how to take the... So if I have cosine, what does that look like? Cosine looks like this. The slope is 0, but on cosine the slope is -1. And so that's going to be negative sine x. So the derivative of cosine x dx is negative sine x. Therefore, if we integrate this dx, then that's going to be cosine. So there you go. The integration of negatives. Oh, and they didn't even want that. But it is good if we're thinking of like taking a derivative of a function, getting the derivative, then integrating that derivative gives you that original function plus a constant. But we just need to take the derivative of a cosine. We need to take derivative of cosine u du. And so if this is cosine u, it's going to be negative sine u. That is going to be the derivative. Hell yeah. So we're going to have negative sine u. Our u is... oh, my bad. Yeah, and you have to do this twice, damn it. So we're going to go u prime is 2x. I can't take the derivative of this because it's cosine 2x. So I'm going to put that as... So now I have u is cosine u prime. And the derivative of this with respect to x is the derivative of this with respect to u prime. Derivative of u prime with respect to x. See how these cancel? And so this still is, a multiplication. So we're going to take the derivative of u prime with respect to x. Let's put that in the parentheses. The derivative of 2x with respect to x. Break out the 2, it's just 2. You know what I mean? We've done that one before in this video. So this value is 2. The derivative of cosine, we know what that is. That's negative sine. So we have negative sine of u prime. Let's just keep that, and then times 2. U prime is 2x, so we have negative sine 2x. I'm going to put the 2 out there. So that is du dx. So du dx is negative 2 sine 2x. Solve for dx. dx. Can we do a little faster? Probably not. It's very difficult. Get this upstairs, get all this downstairs. I'm going to have a negative 1/2, and then I'm going to have a 1 divided by sine 2x, and then a du. So now we're going to plug that in. Our u was this. This was our u. So we're going to have integration of sine 2x u, and then this is what we're subbing in. We're going to have a negative 1/2, a 1 divided by sine 2x, and then a du. These cancel, and then and then we're going to have this integration 1/2 outside. So we're going to have negative 1/2 integration of u du. And this one is going to be a different problem because we're actually going to have it in terms... Yes, it's fascinating, but it's going to yield the same... So yeah, this is I think, a problem that can yield the same values. And maybe we'll graph this one. Okay, but we're just going to integrate this. U, the power goes up to 2, and then we drop down, and then we divide by 2. So we're going to have negative 1/4 u squared plus a constant, which is negative 1/4. Our u value is cosine 2x squared. And then we have plus a constant. So that is the integration of that. So yeah, let's put these into our calculator because I'm really interested in this one. I'm just going to make sure we're in radians. And we're going to do this one. We're going to go sine 2x, cosine 2x. And then we're going to do this negative 0.25 cosine 2x all squared. Hell yeah. And let's see. What was the other one that we actually got? This one. 0.25 sine 2x. Whoops. 2x squared. And I think it's because, you know what I mean? You know why this will work out? And I can even just do it like right now. Is if you have a triangle where your hypotenuse is 1, and then this is your angle. This is going to be sine theta. This is going to be cosine theta. So and let's say your angle is 2x. So you have 2x here and then 2x. That part doesn't really matter. But what we have, if I want to get this in terms of cosine, we know that your hypotenuse squared is equal to sine 2x squared plus cosine 2x squared. And then so if I want to replace this with a cosine, oh, that's going to be interesting. Yeah, okay, yeah, because if I do that, I'm going to put if I solve this for sine, I'm going to have 1 minus cosine 2x squared, and that's going to go right into, well, I don't know, yeah. No, that's gonna take up this. It's going to be 1/4, it's going to be 1/4, and I'm going to have this 1/4, I'm going to have negative 1/4 cosine 2x squared, but then it seems like I pick up this 1/4, but that gets absorbed by this constant, and so that's where that constant gets absorbed. So it'll be kind of interesting. So these last two, they should be offset by a little bit, but they should be the same graphs, where if you found the slope, because we found the integral. The integral says, cool, we found an equation. And then that equation, if you took the derivative, would give us the slope should be the same. This is the derivative of both of those integrals. And so that's what we should see. And I'm going to zoom in the hell on this. All right, zoom in. All right, hell yeah. Oh, I guess this has to graph, but the other two graphs should be the same. Yeah, we really need to zoom in. We will. Do a little box hola. Oh, too big, but anyway. All right, so let's see if those other two graphs, I'm going to get some water. Hell yeah. So now they have the same slope, and that's the trick about math and physics, to be like, I don't care about learning new material. I want to just know what the hell I was taught and why it was taught in just like the speediest, stupidest way possible. Whereas just like, no student should be confused. There should always be little building blocks and little tricks, even if it's just like, oh damn, do these 10 worksheets. You know what I mean? But every worksheet should be little building blocks. Like, I don't know how to do it, because like, one, I don't like the terminology, especially with physics. Oh man, everything's named after a dude, and it's just like, oh, this is awful. Not the fact that it's named after a dude, it's just, it has no relevance to the actual what is going on. But yeah, so that's even the fundamental theorem of calculus, that's not named after anyone, and it's still, there is no description that even gets you close to the actual definition of the fundamental theorem of calculus. You know, you might as well just say you're going to fail the class theorem of calculus. Alright, hell yeah. Alright, so we did that one thoroughly. One more, and then I got to call it a video, because this thing's getting over. We're over an hour probably now. Alright, so we're going to do the integration of tangent x secant squared x. So you do these because you know how to differentiate. If you can differentiate one, I mean, because if you put something in terms of u and you differentiate it, it's not that you'll get the other thing, it's that you'll cancel it. You know, that's where I just need to actually get better. Like, when we do this dx is equal to something something du, we got it to there. Well, for this one, that something something is going to be 1 over the secant squared of x du. And so I'm going to have u as tangent x. And then when I do that derivative of tangent, that's the secret sauce, I get and I do this du dx, and then I get, what do I get? I get secant squared x. That's the derivative of tangent. And I don't know that. I don't even care to know it. But I do know the fundamentals of taking the derivatives of the common ones. So that'll be kind of the master class that we're going to do in the next 5 minutes. But anyway, so that's the gist. Solve for dx, then this cancels, and we pick up a du. Then we get the integral of u to the 1/2 du, and then it's super simple. Power goes up by 1, and then we're going to divide by a 1/2. I'm sorry. We would divide by 1/2 plus 1. That's the power rule. Power rule says if you're going to integrate this, you go 1/2 plus 1 upstairs divided by 1/2 plus 1 downstairs, plus a constant. So that's going to be u to the 3/2 divided by 3/2, which is 2/3 u to the 3/2, just the reciprocal. The 3 stays downstairs. Do you see how the 3 stays downstairs? 2 gets popped up. All right, plus a constant. All right, so let's get a freshie, and let's tackle this and be done. Hola. And then I'll just try to, for this student, I'm going to come back. This is my first round with this student, and we're going to come back and, I don't know, probably just do them in just kind of one page, and then just kind of like, hey, this is, I need to get better at being like, we're going to do this in 2 minutes, maybe 4, but not 2 hours. It's kind of insane. All right, so hell yeah. So our u is tangent x. Why I'm good at tangent of x is because I know that tangent of x is sine x, cosine x. And then if this is my u, I need to find the derivative. I need to find du dx. Well, cool. It's in x, and let's say I don't know how to take the derivative of tangent x. I could look it up, but don't want to. I want to know that I know the fundamentals. The fundamentals are taking derivatives of sines and cosines, and we showed that we don't even need to know how to take the integrals because it's, and maybe I didn't explain that, but 25, how do you know that? This is in the end of the video. We start, and then we kind of go down these rabbit holes. But yeah, you know that's 5, but no, this one has no clean solution. It's a what times what is equal to 25. That's all square roots. Cubed roots are what times what times what. It's even more tricky. And, you just guess. Guess 4. That's 16. Guess 6. That's 36. So 5 it is. All right, hell yeah. So that's the whole idea of integrations, is boosting your knowledge of differentiating and knowing. So this is where you want to put all your emphasis. Knowing that integration is a simple process. Simple, or as in a lot of, there's some integrals you can't do. You get into differential equations, and you'll run into plenty of trickiness. But, for the most part, and what am I saying? Differentiation. Differentiation always has like a plug and chug method to get there. Hell yeah. All right, so the way you could use quotient rule and get there right away. Quotient rule, I don't want to use quotient rule. I want to use the product rule, because I think it might be a good check on the quotient rule, and it can, because all you have to know now is the product rule of differentiation. So if I'm going to, and we need some differentiation terms. If I'm going to differentiate this, it's a product of two things. And it's the first times the derivative of the second, plus the second times the derivative of a first. Because you have a plus sign, it doesn't matter if you took the second times the derivative of the first, plus the first times the derivative of the second. Hopefully I said that in a different way. Where the quotient rule, you might mess up. I'm going to say it correctly, but I don't know. I'm not 100%. I think I'm 100% because I just did it the other day, but see how it's going to be low d high minus high d low, all divided by the square of what below. The square of what's below, cool, I can always do that, but is it low d high, minus high d low? Because of the minus, you'll be off by a negative if you did high d low minus, or I don't even know what you'd be off. I don't know enough about math theory to be like, would I just be off by a negative sign or a whole lot more? Where the product rule, because it's a plus sign, you can't go wrong. It gets a little uglier, but all you have to do is just combine fractions, and that's a good skill as well. So here we go. And we're going to know that we're going to use our here's sine. The derivative is, I'm going to do sine and cosine. So here's sine, here's cosine. And the derivative of this, so the derivative of sine is cosine x. The derivative of cosine, this has a slope of 0, a slope of -1. So it's going to be negative sine x. So the derivative of cosine x dx is negative sine x. And now we can prove it. It's the only two you need to know for this one. So the first times the derivative of the second. We're going to have sine x. We're going to take the derivative of this. We need to bring down the power, -1. And now we, and we're using the power. Even right now we're using a u substitution. We're saying, you know, I'm going to say w. W is equal to cosine x. And I have w to the -1. And then, so what's the derivative of this with respect to w? It's going to be the power rule. Bring down the -1, w. Oh, well, actually, we don't have that. We want to take the derivative of w with respect to x. Where w is cosine x. I'm sorry, yeah. We want to take the derivative of... No, w is going to be, oh, hell. I'm sorry. But, how you would set this up is you would have to say this is, let's just use u. Let's say u is cosine x. So this is u to the -1. I need to know the derivative of this with respect to x. Hey, this value and that aren't the same, so I'm going to use chain rule. I'm going to say it's the derivative of u to the -1 divided by the derivative of u, and then du dx, which I can do. So this is the power rule of here. 1, drop the power by 1, so that's there, did that one. And du dx is the derivative of u, and u is going to be cosine x. The derivative of cosine x is a negative sine x. -1 sine x. Put back in the u, so we have the negatives cancel. We're going to have a sine x on top, and we're going to divide by cosine x squared. That's what we should get using u substitution. I think it's just a lot simpler to just do it like this. So we have sine x, bring down the power, take the inside to a -2, drop the power there, and then take the derivative of the inside. Derivative of cosine is negative sine, so -1 sine x. We get the same thing. So here we're going to have a sine x squared. And then even this, we forgot a term. We forgot that term, which was our other negative sign. No, there's our negative sign. Yeah, I'm sorry, but should we have sine x or sine x? Oh, no. So this was just taking the derivative of that part. So that's what we would get. The product rule says the first times the derivative of that. So that's where we pick up this other sine squared. So we're going to have sine x squared. The negatives cancel, divided by cosine x squared. Hell yeah. So that's going to be the first term. The second term is going to be the second. Maybe grab a little sheet of paper. This is going to be the second, which is cosine x to the -1. Take the derivative of the first, which is just cosine. Slope of 1, slope of 0, 1, 0. The values of cosine are 1 and 0 at those two locations. So the derivative of that is going to be cosine x. This is just cosine x divided by cosine x, which is 1. Okay, sweet. So we have 1. And then we just took the derivative of that. Okay, so hell yeah. And so what do we have here? This is tangent squared plus 1. I feel like we did something wrong. No, we took the derivative of tangent. All right, so let's say we messed up. that's where we can use a second. We're going to take the quotient rule, which is low d high minus high d low, all divided by the square of what's below, and see if we can find our error. So we're going to take low cosine x, derivative of sine, which is cosine x, minus, so it's low d high minus high d low. Derivative of cosine is a negative sine, so we're going to get that. Cool. And then that's all divided by cosine x squared. This is sine squared cosine squared, which we know is sine x cosine x 1, which is equal to 1. Pythagorean's theorem, and we have 1 divided by cosine x squared. So that is the derivative of tangent. Derivative of tangent x is that. So where did we go wrong here? So let's go through this one like one more time again, just to see. So the product rule is first times the derivative of the second. And then the derivative of the inside is a negative sign. Plus the second times the derivative of the first, which is cosine. So this term becomes 1, and then this becomes sine x squared divided by cosine. Sine x squared divided by cosine x squared. Oh yeah, so it is. It's just one of those things that this is, these are one of the properties where it's just like, okay, so if you do have this, sine x, cosine x, and 1, let's see if Pythagorean theorem works. Because what we can do with this 1 is we can say it's cosine x squared divided by cosine x squared. So that's what we can do. Yeah, we don't even have to break this out. So if you do product rule, make sure your denominators are the same to get it looking like the quotient rule, especially for trigonometric functions, because then you're going to have sine x squared plus cosine x squared divided by cosine x squared. And then so that's where the Pythagorean theorem says that's 1, and you have 1 divided by cosine squared, which is secant x squared, or written like this. Hell yeah. So there you go. So that was brutal. So let's grab a new sheet of paper. And so u is tangent x, du dx is secant squared x, and then this is the integral. This is what we're given, and then so solve for dx. Get dx upstairs. Dx is 1 divided by this secant squared x du, and we're going to sub that into here. So our u substitution says this is u to the 1/2. Cool. We still have this secant squared x, but we're going to sub this dx, and we're going to have 1 divided by secant squared x du. So that's where those cancel, and we're left with this, which we can take the integral of. And so it's just the power goes up by 1, and then 1/2 plus 1. That's the power rule of integration plus a constant. And so we have u to the 3/2. This was going to be 3/2 downstairs. That's 2/3 plus a constant. And so now we have our final answer of 2/3. Our u is tangent to the 3/2 plus a constant. And we did it. Hell yeah. And, I don't know. I mean, we went hella on this one. Should we take the derivative of this? You know what I mean? Or we're gonna say, hey, I can't take the I'm gonna do u substitution, so I'm gonna say this is the derivative of 2/3. I'm gonna get the constant out. Derivative of u to the 3/2 du. Cool. And so that's gonna be the derivative is bring down the power, so that's going to be 3/2. That's cancels, and this gets dropped by 1. So I'm going to have u to the 1/2. But also, I need, sorry about this, I need the derivative of this with respect to x. I can't do that, so I'm going to do du and then du dx. And then so if my u is tangent x is my u in this case, then du dx is this term, and the derivative of that, we already did it, 1 was just secant squared x. Not going to do it again, but we did it thoroughly with the product rule and the chain rule, so now I can feel confident that I can do it quickly, and put that value in. So this is going to be just u to the 1/2, and then we pick up that term, that secant squared x, and that's going to be the square root of tangent x, and then secant squared x. Alright, hell yeah. So anyway, that's 4 problems done in my style. You know, try to do as much teaching, because I'm teaching myself as well, and that's kind of cool. Alright, so we did it. And then all of those you can check using graphs, if you kind of know what the hell that means. So if you find the integral of this, you know, that's going to be your... Hell yeah. I mean, if this was the integral of x squared, then it's going to be 1/3 x cubed. If you had this is your equation that looks like that, let's say, and let's say you get to this point, x is equal to 2, and you go right there. It's not the value. This value don't mean nothing, but the slope of this line, if you use a solver or just even change x by a little bit, like using numerical methods, and find that value of that slope is going to be this equation evaluated at x is equal to 2. And that's where if all you're looking for is the slope, that's where this equation can be anywhere. You know, does that make sense? Because now this is the integral. It could be up there, and you're still taking x is equal to 2. What's the slope? The slope of this is when you plug x equals 2 into that derivative. Hell yeah, and that's a pen drop right there. So I'm going to take a little break. We're done with this video. But maybe I'll do a sheet of paper where I can kick these out in like 2 minutes per pop. That'd be real tricky. No, but you just give the answer. But I think this video, and then so this video is not over, because I'm going to also put where I started on this video, and we do go over some good stuff. But hell yeah. So that was my effort for tonight. Looks like it's a 2-hour video, but hopefully at the beginning it can be a under 10-minute video. Booyah. Alright, hell yeah. So I'm asked to do these 4 problems, and this is for a college student, and a college student doesn't have much time, so we're just going to go through this. And this is cool, because you're going to see me do this fast to me, because I'm thinking we should go over all the derivatives of all the trigonometric functions and figure out, you know, how they relate to their integrals. But hell yeah, we're going to do u substitution, so let's just fly this one out. The first problem is cosine 8x dx. So let's do that. Hell yeah. So we're going to have the integral of cosine 8x dx. And then I can just teach on the fly, because you know, prerequisite coming into this, we need to know that the integral of cosine x dx is something that we actually know. And so here's the first fundamental point of integration is like finding the square root of 25. How do we know that? Just because we know it. You know what I mean? We know it's 5. And there's a lot of things in math that are like, how do you do this? Well, this is saying that we have something times something is 25. And it just happens to be 5 times 5 satisfies this. But that is not what we're used to. At some point in your mathematic kind of progress, and this can even happen at high school, because this happens pretty early on, is things aren't just 5 plus 5, 5 minus 5, 5 divided by 5, 5 times 5. Straightforward, this, do something with it, get on to the next thing, where it's kind of like a roundabout way. Logarithms are like this. Okay, hell yeah. Let's not get derailed too much. But to do integrals, we know that when we do find this integral, hell yeah, that once we have it, we could take the derivative of it. So we're, you know what I mean, we're in trig world, you know what I mean? So this is where it's just like, let's start tagging these. And we don't have to tag, you know, even tangent, secant, cotangent, cosecant. Let's just do sine and cosine. So we're going to, I'm going to first draw sine and cosine. And the easiest way to do it is just draw quick drawings of this. Where this is sine of x and this is cosine x. Sine x starts at 0. And then when you get out to, you know, 90 degrees, or if you're a math major, pi over 2 radians, what happens to sine x? It goes to 1. And this starts, and cosine x starts at 1 and goes to 0. And so what we have is, we're just looking at the slope, doing a visual look at the slope. This is a slope of 1, and this value over here is 1. Cool, so that checks. This slope right here is 0. This value right there is 0. So we can say that the derivative of sine x dx is this cosine function. Hell yeah. Now what's the derivative of the cosine function? And this one you got to be careful of. The slope right here is 0. Cool. Sine x is 0. But guess what? The slope right here is negative 1. And sine x is positive 1. But we could just, you know what I mean, do the reflection of it. Hey, this is negative sine x. Slope of 0, this is 0. Slope of negative 1, this is negative 1. So this is where this is sine x. Now what we can say is we can say, hey, if the derivative of this function was this, like, and then even for me it gets kind of like headachy. Is like, okay, what the hell does this mean? It means that the integral of cosine x is, you know, integral cosine x dx is sine x. And why is that the case? Because if I integrated this function, and now this is like what's providing the area under the curve and all that integration stuff, if I took the derivative of this, derivative of sine x dx, guess what I get? And then, you know, draw the little graph. There's sine x, the derivative of it, 1 and 0, that's going to be that cosine x, because cosine of 0 is 1, and then cosine of like 90 or pi over 2 is 0. Hell yeah. Okay, so so we took the integral. The derivative was cosine. Hell yeah. So that means that yeah, and still that mentally is very difficult for me. Integrating cosine, we get, you know, this is like taking x and integrating it and then getting x squared, 1/2 x squared. Taking the derivative of this is bring down the power, 1/2, bring down the power, x, drop the power by 1, and we get x again. And so this is like that. And then so if we took the derivative of it, we would be back to the original function. Original function, take the integral of it, we get sine x, take the derivative of that. And here is where I will, you know, I mean, we're trying to get to the problems, but hell yeah. If we said this is the integration of this is sine x, we can add this constant here. Because if we take the derivative of sine x dx, if we take the derivative of sine x plus a constant dx, a few rules that we can use, and it's good to use these rules. We can take first the derivative of sine x dx plus the derivative of this constant dx. This constant, what we know about derivatives is that constant can come out. And so really techie, you would do this. Derivative of 1 with respect to dx. And then, how about this? So you would do this, and this just becomes 0. And what this says is as you change x goes, this is your independent variable, 1, 2, 3. Hey, this isn't even really a function of x. You could say, and this is where in the other video I did, and sorry about this, I can't help myself from teaching because it's the fundamentals of like this kind of stuff that's like, hey, what the hell does this even mean? It means that we have a function. you think of this number as a function. This is y is equal to 1. And then here's your x values. These are what you're changing. That's how the derivative works. And if like, hey, I changed from 0 to 1 to 2, what did this change? Well, that stayed 1, that stayed 1, that stayed 1. So the change in this, you can say the change in this function of 1. And then you could say that this is a line. So this is the other day I was doing this. A line is y is equal to mx plus b. This is going to be 0, slope of 0x plus b. So this right here could be 0x plus 1. And I think that really helps. I think the struggle is real when it comes down to integrating and differentiating down to like the building blocks. To be like, you know, instead of just hand waving this, that the derivative of a constant is 0, like why is it 0? It's because of this. So now when we change this x value, because this is also the change in this formula compared to the change in just changing x. So let's do that. At 0, so we're going to go from x, the change in x could be, 0 to 1. So that's 1 minus 0. You do it in reverse. And then if this is 1, well, this, whether this is 1 or 0, this is always going to be 0. And then so we're going to have 1 minus 1. And we're going to have 0. So that's, hell yeah. I think that was worthwhile to do that. And that really shows how, you know what I mean? Because I've gone my entire career with just being like, just putting this in as a constant and just totally forgetting about it. But if you think of this as, well, and that's almost where I think more study needs to be on the superposition, because we just took a derivative that was sine x plus c and then split it up using the rules of differentiation, that you can take the differentiation of this part plus the differentiation of this, and then you can even pop out the constant and put a 1 here and do that same process that we did. So you do have a superposition, and hell yeah. So a lot more emphasis needs to be put on differentiation going into integration, and I think it is, but then the second you're starting to do integration, like no one's like going back and being like, hey, let's take a look at the differentiation components. All right, hell yeah. So yeah, that whole thing, this whole intro could be at the end, you know what I mean? But we'll see what we want to do, because that's 10 minutes. Alright, hell yeah. And then what did we even learn in that 10 minutes? We learned that the integration of cosine, I can now see that if I'm differentiating this side and get this, then integrating this side gets that. So when I integrate this, I go to there. So we're in the chapter of integration, so I'm going to say, hey, when I integrate that, I get that function. And so when I integrate this, I could also have a constant here. And that's where to figure out these integrals, the integral of negative sine x, the integral of cosine x, and that really shows that, the fundamental is the integral of negative sine x gets to cosine x. The fundamental of integral of cosine x gets to sine x. And so prior to, doing these problems, I definitely sat down and wrote, here's the graph of sine x, here's the graph of negative sine x, here's the graph of cosine x, here's the graph of negative cosine x. Let's figure out what the slope of this one is. Slope starts at 1, ends at 0. What function starts at 1? Cosine does. And ends at 0. Cosine does. Hell yeah. So the derivative of sine x is cosine x. And now I know that if I integrate this plus a constant, I get that. Hell yeah. So that's exactly like taking the square root of 25 and being like, what times what is 25? Is it 4 times 4 is 16? No. Is it 6 times 6 is 36? We're getting closer. You know what I mean? Hell yeah. Okay, so now the next one. Integration of negative sine x. We have a slope of negative 1. So that should, scream negative cosine x. And then we have a slope of 0. Hell yeah. And so the slope of this is the differentiation of this equation. So so taking the derivative of negative sine x when we change x is going to be negative cosine x. Therefore, the integral of negative cosine x plus c is this. But that's where I'm showing you the 4 different ones you'll come across. This is taking, we want to be able to integrate sine x and cosine x. And, but like I said, it's like this. Don't think of it as integration. Find all 4 derivatives of derivative of sine x, negative sine x, cosine x, negative cosine x, and now you have the integrals the other way. And that's where, you know what I mean, because at some point we're just going to get a hand waving. You know what I mean? Did we even get one? Hell yeah. So the integration of cosine x is sine x. And instead of memorization, now you know. Like and then, because even if I'm right here, I'm just like, how do I do this? Well, let's just choose one. Sine goes to there. The derivative is 1 and 0. That's cosine x. It's a positive slope the entire way, so booyah. Therefore, the integration of this plus c is sine x. And then, so therefore, the integration of cosine x is sine x. And booyah, that one we just lucked out. It was the first one. But let's go through the rest of these. The derivative of cosine x. So here is the cosine, and it's got a slope of 0. That should say the value of this, when x is 0, the slope of this equation of cosine x is 0. So what trigonometric formula, when you put in x is 0, output 0? Sine x. Cool. But also negative sine x. So let's go to the next part. So if we have cosine x, right here the slope is negative 1. And so there you go. So we're going to be negative cosine x. Holy hell. Messed that one up. This is cosine x. It starts at 1 and goes to the 0. The slopes are 0 and the slopes are negative 1. What starts at 0 and goes to negative 1 or positive 1, that's kind of like your sine x. And because it goes to negative 1, that's going to be negative sine x. So there you go. Negative sine x, the integral plus the constant is that. All right, let's take some juice. All right, hell yeah. And then the next one. So we're going to have negative cosine x. Starts at negative 1, goes to 0. The slope here is 0. What starts at 0? Any of the signs, negative and positive sign. But then it has a positive 1 slope. So the derivative of negative cosine x is sine x. Therefore, the integral, and even this whole chart says, hey, take the derivatives, because derivatives are straightforward and easy. And I can make these straightforward and easy. I don't know. I don't watch a lot of math and physics videos, but I mean, that's where I think the fact that we're doing integration in Trig world, like instead of just looking at this chart, I think, doing all of these. So we just did those. We did all 4 combinations of cosine, negative sine, and positive sine. Even though if you know 2, because integration and differentiation, all constants can be outside, whether there's a negative 1 outside there. Okay, hell yeah. Alright, hell yeah. Okay, so a college engineering student is in mechanical engineering taking calculus and second year. And so going over integration using U substitution, and integration requires you to kind of understand what differentiation is. And so this is the second take of this video. We started out, but we go down rabbit holes of learning. And so we went all over the integrations of sines and cosines, and that's going to be at the end of this video. But I think for this student, they just want, with under 20 minutes, they want these 4 problems done. And so that's what we're going to do. And I'm going to try to do as much education on the fly. But what happens is the second I go down something, I want to do like an hour lecture. You know what I mean? Even just for me, just so I know I'm solid. Okay, hell yeah. But the first one up is integration of cosine 8x dx. And I said, from the, where we got down the rabbit hole, I got to here. I got the, well, let's just figure out what the integration of cosine x dx is. And how do we know this? How do we know this is because of, we know that, finding the differentiating trig terms yields an equation, and then the opposite is, the integration part. So here's how we do it. I'm going to draw the sine graph, and even at the end, I didn't do it like this. If you're going to draw a sine graph, do 3 hash marks. It's 30, 60, 90, or you could do it in radians. Do equal hashes, so you have kind of like a square there, and this is 1, this is a half, and what you'll have is this. This is the linear approximation for sine, and it looks like that, or you could just draw it, quickly like that. That's how we've been doing it. But cosine, you know what I mean? Do 3, 30, 60, 90, and then kind of equal, and what you'll have on cosine is you'll get to here, and then you're going to drop down. And so this is what we have, and then the curve follows that line, and it kind of circumscribes that line. And this is cosine x. And so we'll just go over this one because it gets us there. We're gonna take the derivative of sine x dx. And what this says is what's the slope at kind of each of these points along here. We're going to take the slope at the beginning and the end. The slope at the beginning is 1. The slope at the end is 0. So knowing that we know sine x and cosine x, what function, when you input x is 0, yields 1? Well, that's what cosine does. Cosine of 0 is 1. And then how about at 90 degrees? And I'm just going to stick with degrees in here. You know what I mean? I'm not there. I'm not a mathematician where it's just like pi over 2 radians makes me feel, good or anything like that. But anyway, so add sine of 90. Well, that's going to be 1. And it's going to have a slope of 0. So what equation, when we'd say, cosine of 90 is 0? And so that shows that that's the slope. So cool, we did it. So the derivative of sine x dx is cosine x. And this is where we can say that we can add any constant, because if I take the integral of this, oh man. Oh, did I mess up? Alright, hell yeah. I have to show my error. And that's why this stuff is so heady. Oh man, I gotta get my chair. I've got a raft in this room. Alright, hell yeah. So no, this doesn't make sense. The integration of a constant, no, that's going to be like x, constant x or something like that. And so this constant has to be over here. My bad. When we differentiate sine x plus a constant, then we get cosine x. So when we have the integration of cosine x dx, this yields sine x plus the constant. So these constants are over here. But this is good for me, and hopefully we can put this part at the end of the video. And I'm so bad at just flying these out, so I'm going to do this student a solid, and we're going to do it. Shoot even just for 10 minutes. We can always add more later at the end. Holy hell, I'm bad at this.